Ever think about the hidden languages that run our world? Not English or Spanish, but something more fundamental. Today, we're going to decode one of them, the language of power itself. And believe it or not, our guide for this is an engineer's solutions manual for electric machinery. So let's dive in. Okay, so you look at something like this, and yeah, it's a lot. It looks totally impenetrable, right? Just this wall of symbols, numbers, and Greek letters. It's kind of intimidating, and you're probably thinking, what on earth am I even looking at? But here's the thing. What if this isn't just a jumble of math? What if this is a language? A super precise descriptive language that engineers use to, well, to build and run the entire electrical grid that we depend on every single day. That's exactly what we're here to figure out. So, like any language, this one has rules. It has a grammar. And in the language of power, that grammar, well, it's all about equations. Now, don't let the word equations scare you off. Think of them less like a pop quiz in algebra and more like a recipe. Seriously, they're a set of instructions that lets an engineer predict exactly how electricity is going to act in a circuit or a massive generator or even the whole power grid, all before a single wire is even laid. So, what kind of stuff do these recipes calculate? Well, a really important one is something called the power factor. You can just think of it as an efficiency score. It tells you how much of the electricity zipping down a wire is actually doing something useful, like lighting up your room, versus how much is just getting wasted along the way. And this is like a perfect sentence written in that language. It tells a whole story. See, this first bit here, that's describing the total potential power you've got to work with. Then this next part brings in that power factor we were just talking about, our efficiency score. And this last piece, that describes how the power actually pulses back and forth in a normal AC circuit, the kind you have at home. Every single symbol has a job, and when you put them all together, you get a crystal clear engineering story. Okay, so equations are the grammar, but how do you see the big picture? I mean, how do you visualize it all? That's where diagrams come in. They're basically the blueprints of this language. Take a look at this. It's called a one-line diagram, and it's straight out of our manual. Now, it might just look like a bunch of lines and little symbols, but this thing is a universal map. For real. An engineer in Tokyo could look at this, and an engineer in Berlin or Sao Paulo could look at the exact same diagram, and they'd both know the entire story of how electricity is moving through the system. And that's absolutely critical, right? It means parts made all over the world can work together safely, and any engineer can help fix a problem, no matter where they are. And you know what's cool? That whole complex-looking map really just boils down to a simple four-step journey. First, you've got generation, where the power is made. Then, transmission. That's it traveling over those huge power lines. Next is distribution, where it's delivered to our neighborhoods. And finally, you have the load, which is just a fancy engineering word for, well, for us, for our homes, our businesses, for anything and everything that gets plugged into a wall. But things don't stop there. In the modern world, there's a third crucial part to this language. It's the part that lets engineers kind of light the future. They've become modern-day scribes, but instead of ink, they're using code. And why code? I mean, why bother? Well, the manual actually spells it out for us. It says that for certain kinds of repetitive tasks, doing it all by hand it's too slow, and you're bound to make mistakes. Computers are just way, way better at it. So code isn't just a nice to have, it's an essential tool for getting things done fast and getting them done right. And here's exactly what that looks like in practice. An engineer sits down and writes some code defining all the little details, like the frequency of a generator. And the computer spits out the result, this super precise graph that predicts how different generators will share the electrical load. Think about that. They're basically running a what-if scenario on the computer to see what happens, without having to risk causing an actual blackout in the real world. Incredible. So when you put it all together, you've got these three parts of one single, incredibly powerful language. Let's just quickly recap how they all fit together to literally engineer the world we live in. First, you've got the grammar array. Those are the equations, the fundamental rules of how electricity works. Then you've got the blueprints, the diagrams that give everyone a universal map to follow. And finally, you have the modern scribe. That's the code that lets us simulate, test, and perfect our designs with a level of precision that was unimaginable just a few decades ago. So really, the next time you just flick a light switch, take a second to think about that journey. It all started with a language that looks completely abstract, just symbols on a page. But that language gets translated through equations and through diagrams and through code into the invisible, reliable power that just works. It's the force that underpins pretty much everything in our modern lives. Kind of makes you wonder, doesn't it? We just decoded one hidden language today. What other kinds of invisible engineering are out there? What other incredibly complex systems are hiding right in front of us, just waiting for someone to notice? Makes you think. What are you going to notice next?